All right. Well, hello, this is Matt Roscoe, and I have a lecture here, a video lecture for Section 3.9 on linear approximation in our course Math 171, Calculus 1 at the University of Montana. All right, so let's just get right to it. So today what I want to do is show you the concept of local linearization just pictorially, just so you have a picture in your head of what we're doing, and then we'll go ahead and take a look at a dynamic graphical representation, so using Desmos, and then just talk about what this means in an algebraic sense, and I'll do just one full-blown example and we'll call it a day. All right, so this is your picture of local linearization, I guess, pictorially. Let's make it bigger, I guess. So the idea is that we have some function in black. Here I think what we see is the sine curve. And we can think about it, the behavior of the function in a local sense. So around this point right here in the middle, where x is equal to 0, as a line. And to make this more apparent to you, one thing you might think about is zooming in there at that point. So I'll zoom in here, and oops, wrong direction. I'll zoom in here. There we go. So now we can see the red line getting very, very close to the black function, at least in the neighborhood of 0. And if I zoom in even one more, so I guess you can see that these 4 boxes here are now these 4 boxes here. Now I can see that the behavior of the sine curve, which is black here, right, is very closely approximated by the behavior of the red curve, right, which is the local linearization of the function. So you should recognize local linearization as nothing more than just the tangent line to the function at the point where we are linearizing the function or estimating the function with a line. So of course this falls squarely into the wheelhouse of calculus, because we've developed a bunch of tools to find slopes of tangent lines of functions, and now we're just going to find those lines and use them as local estimates. You might be asking, like, why in the world would we ever want to do this? And it's because lines are just very easy to understand and deal with in a computational sense. And if we have some function that is really difficult to deal with, but we only need to deal with it in a very small neighborhood, then it makes sense to just use the local linearization, just because computationally it's much easier to work with. Okay, so that's the idea. Local linearization is simply finding the tangent line to a function at a point and using it to estimate the value of the function in that neighborhood. Okay, so let's take a look at what this looks like on Desmos. So I'll go ahead and pull a Desmos graph down, and this of course is available to you on the slides if you want to look at it. So here's a good picture of what we're talking about. So we have some function with a point on the function. The function is red, and we have a tangent line to the function that's in black here. And we can kind of think about, when I get really close to that line, that point, then the line behaves very much like the function, and it's very close to the red line, right? But the further and further I get away from the point where the local linearization is exactly the value of the function, the bigger and bigger the error is. And that's what these two things are supposed to be showing you. So if you kind of scroll down here on the left, you can see that I've given you the local linearization error at x plus d and x equals a plus d and x equals a minus d, where d is controlled by the slider below. So d is just the distance from the point of local linearization that we're inspecting the error. So I can make that either smaller or closer. And what you can kind of see is that the error is really small when I'm up here close to the point of local linearization. In fact, it's less than what, tens, hundreds, thousands. I guess it's in the neighborhood of it. This is 5 thousandths and 5 thousandths away from the function. But that's when I'm very close. But the further and further I get away, of course, those errors grow. So what we're seeing in the blue here is just really the distance between these 2 points, right? And you can see the error is actually not balanced. I mean, it depends on where you put the local linearization. Sometimes it'll be greater before the local linearization or greater after. In this case, we have a higher error here because there's a higher rate of curvature here than there is, I guess, after the point of linearization here. But I hope you get the idea that, we're both concerned with finding these lines that linearize the function in a very local sense, as well as inspecting their errors and trying to get a sense of how good they are, at a certain distance away from the point. All right, I'm going to go ahead and put that away for now. And let's just talk about some of the algebraic representations. So the tangent line to f passing through the point a comma f can be used to approximate the curve of f of x when x is near a. So in other words, when we're in sort of a local neighborhood, that's why it's called local linearization, around some point a, we can find the tangent line and just use it to approximate the curve. So the equation of the tangent line is given by this, y equals f of a plus f prime of a times x minus a. So a linear approximation of f for x near a is given by this function, right? It says that f of x is approximately equal to f of a plus f prime of a times the quantity x minus a. And remember that approximation is, x has to be close to a, so it's in this sort of local neighborhood only that this is a good approximation. We know it's exactly equal to it when it's when you're at a, right? But nearby, it should be close. So the function is called the local linearization of f of f near x equals a, and the local linearization is equal to, I'm sorry, I shouldn't have approximate there. It should be equal to, L of x is equal to f of a plus f prime of a times the quantity x minus a. So you're probably wondering, well, where does that all come from? So let's just make sure you understand why this makes sense for the general form for the line that's tangent to the function when x is equal to a. So let's go ahead and take a look at that. So let's see if I can get over to my overhead. There it is. Okay. So what are we talking about here? I'm going to turn so I can see what I'm writing. Let's first just kind of sketch up what we have, right? Let's draw a general function, right? Let's call this, y, and this is x. And we have some function. I'm going to draw it as a nonlinear function to try to get a sense of what's going on. I'll put an a here because we're picking a point a on the function. So I guess this guy is f of x, right? And we know that if this value is a, then I guess this value right here is f of a. So we have something that kind of looks like this, and what we're after is this slope, I guess this line right here, right? And that line we're calling the local linearization of x, so we'll call it big L of x. And we know that this line approximates this function in this neighborhood around a, right? There's some sort of bracketed neighborhood where these two functions are very close in value. Okay, so that's what we're after. What do we want? We want to know, what this guy's equation is, right? So we want to know what L of x is. And L of x, of course, we know is equal to a line. It's a linear function, so we can think of it as mx plus b. If we can figure out what m and b are, then we're done, right? So right away, it should make sense to you that we know what m has to be. It's got to be the slope of the tangent line to the functions. And since we're building this, local linearization around a, we would want that slope to be the derivative evaluated at a. So I guess it makes sense to me that this would be f prime of a times x plus b, right? Because that would give me the slope of L of x, because it's the slope at that point a. Okay, so let's see. What do we do next? Well, usually the way we do this is we have to find what b is next, right? And the way that we do that is we plug in a point, for x and y here. And the point, we only have one point. It's this one right here, right? And that point is the point a comma f of a, right? It's a, and then a fed into that function. That'll give me the x comma y. So that means that I could find what b is next by plugging in the x and the y. So let's do that next. Let's see, so x comma y, so f of a would be equal to L of x, right? That would be the output when I plug in a as an input. So we would say that f of a must be equal to f prime of a times a itself, I'll just put a parentheses a, plus b, right? So that's basically the way that then we can solve for b. And when we solve for b, what we end up getting for b is what f of a minus f prime of a times a itself. So that piece is b, and we should be able to plug that piece. I'll just put blocks around b's, right? So this piece right here now can be plugged in for b right here, and what we'll get is some equation for the local linearization of x. So I'll do that next. I'll just say plugging that in, we'll end up with L of x is equal to, let's see, so m is f prime of a times x, and then b is just this expression, so I'd say plus f of a minus f prime of a times a. And I don't know if you noticed this, but there's two f primes, right, here and here. So it might make sense to group those and factor out. So if we do that, I'll move the f of a over here. I'll move these two next to each other and factor out the f prime of a. And what's left is x minus a. And so we get the cardinal form for the local linearization of x. It's just f of a plus f prime of a all times x minus a. And that's where that equation comes from that I just showed on the screen. I hope that makes sense. Let's go ahead and go back and see. Yeah, sure enough, and it should be equal here, but f of a plus f prime of a times x minus a was exactly what we got. And so basically this gives us sort of a plug and chug way to simply find the equation of the line that's tangent to a function at a. And we think of that line as the local linearization. I mentioned when we were looking at the graph, I'll pull it down again, of this local linearization phenomenon, that one of the things we're really interested in are these two numbers, right? These are the numbers that tell us, how good is it in estimating the function. It's really good in here. Do you see that? But if I move the function, I guess the point of linearization, say, to a spot where there's more curvature, you can see that, errors are really bad in here. So these sort of differences are something that we would want to pay attention to if we ever were to linearize a function and use local linearization in an application, because we'd know that the black line would not be a very good predictor of the red function, if we were even this far away from the point of linearization, at least if we were in that neighborhood. Now, we'd have no problem if we were in this neighborhood, right? So I hope that makes it clear that, these numbers, these blue numbers, are really important for us to pay attention to. So that's why we make a function out of the error as well. And we say that the local linearization L of x of the function f of x at x equals a is error prone as x moves away from a. So the error in the approximation, we're going to call that e of x, is just defined as the difference between the function at x minus the linearization at x. And if we plug the linearization at x in there, the thing that we just found, we'll end up with f of x minus f of a minus f prime of a times x minus a. Let's do just a quick little lesson on why that makes sense. So what are we talking about in error? Well, here the idea, I'm going to draw the same exact picture as I drew last time here. Draw y, draw x, put in an a. I don't know, let's say the function goes right through there, so something like this. So this would be our f of x that we're approximating with a a tangent line here that we will call L of x, local linearization. And so we would think that there should be some function that will tell us, that we could plug in x that will tell us how far away these two are at a certain x, right? And that function, so really what we're looking at is the difference between here and here, right? We call this e of x, right? And I could slide that anywhere I want based on, which x I plug into the error function, right? And it's pretty easy to see then that, if you want to know the error function here, e of x, well, maybe it's not easy to see, but I will say it seems to be intuitive that what we want to know is the difference between those two functions, right? I mean, we just want to know what's the difference from f of x to L of x for that value of x, right? So that will tell me basically how tall that little bar is, right? Plugging in what L of x is, we'd have f of x minus curly brackets f of a plus f prime of a times x minus a in curly brackets. So if we subtract the whole thing, what we'll end up with is f of x minus f of a minus f prime of a times x minus a. And I believe that was the equation that we just showed on the screen. And it's a nice, I guess, easy way then to just plug in and get an error function that then you can just say, well, what happens when I'm not at a, I'm at a plus 1, right? I can put a plus 1 in here and feed it through function and error and local linearization, define this way and get an answer. Okay, so let's go ahead and move on and talk a little bit about an actual example. So I want to spend some time doing this example, and I think it pretty much covers the bases on this chapter. Let's go ahead and see what we can do with this one. So it says, consider the function f of x equals x to the third minus 3x squared plus 3x plus 1 near x equals 2. Sketch a graph, sketch the local linearization of f of x at x equal 2, find the equation of the local linearization of f at x equals 2, and then find the exact value of the error associated with the use of the local linearization to estimate f of 1.5. So I guess we're going to be a half a unit away from where the linearization is tangent. And then show where this error can be found on the sketch you drew in part A. I guess it's in part 1. So let's do this one as if we don't have I guess anything. Well, first I'm going to go ahead and get a Desmos graph to do this, because I don't want to hand plot this, right? You would never want to hand plot this, but let's just do this. Let me write the function down. So the function is f of x equals x raised to the third minus 3x raised to the second plus 3x plus 1. Okay, so there it is. And what we're looking is for the local linearization at 2, at x equals 2. So at this point right here, so I probably should figure out what f of 2 is. Well, f of 2 is 3. So that means that I should be able to plot the point 2, comma 3, and it should be on the function. Okay, so this is where we're going to form our local linearization. In other words, we're looking for the tangent line to the function right there. It looks just at first glance like it's going to be fairly accurate in a neighborhood that's pretty close in here. But boy, by the time I'm down here, it's going to be very inaccurate. So our goal is to find both the equation of the tangent line through the green point, and then to evaluate its error at 1.5. So let's see if we can figure that out. I'm going to switch back over and take a look at what I'm supposed to do. So I'm supposed to first sketch a graph of the function. So this would be sort of, I guess I won't label it, but let's sketch the graph of the function first. So when I looked at the function, I noticed that, I need 1, 2, because 2 is the targeted area of linearization. One of the things I noticed is it went through 1, comma 2. So 1, 2, so sort of 1 comma. Oh, maybe I'll do it this way. Maybe I'll make it. Let's see. So yeah, let's go 1, 2, 3, something like that. So 1 comma 2 was here, and the linearization was at 2 comma 3, which is right here. And it had a y-intercept of 1. So those are 3 points on the graph. I think it kind of came up like this, and then went up like that, something like that. So this is our f of x, y, x. And we're supposed to sketch the local linearization. So, I mean, what do we mean by that? We just fancy name for a tangent line to the function at that point, right? So just a sketch of the local linearization. I don't know if that's even a straight line, but and I don't like how closely f of x and L of x are together here. So I guess what I would probably do is I would say, this one's f of x here, and this one here is L of x. I hope that makes sense. So, I mean, at least what it does is it helps us get a sense of, okay, if we're going to go after this local linearization, we expect something with a positive slope and a negative y-intercept. I think that's the reason why this book problem asks you to sketch it first, because you kind of want to know what you're shooting for before you dive in with the algebra. Okay, so we've got to sketch the function, we've got to sketch the local linearization. Let's see, what else was I being asked for? Let's get this out of the way for now. Find the equation of the local linearization of f at x equals 2. Okay, so we're trying to find the equation of the tangent line right there. Let's go ahead and see what happens here. So we're trying to find the equation of the tangent line, and we could do this by brute force, right? We could find the slope of the line. We know it goes through this point 2 comma 3, right? This is 1, 2, 3. So given the slope and a point, we could do it that way. But let's go ahead and use the work that we just developed. We know that the local linearization L of x is equal to f of a, right, plus f prime of a all times x minus a, right? So generally this is the case. Here we have what a is equal to 2. We know what f of well, we'll need to find f of a, so let's see, f of 2, so I'll plug that into the function itself. So what is the function again? I didn't even really write it down here. F of x is equal to x to the third minus 3x squared plus 3x minus 1. So let's see, f of 2, which is this piece right here, would be 2 to the third minus 3 times 2 squared plus 3 times 2 minus 1. I've already done this, so I'll just tell you that, f of 2 is 3, right? We also just did that on Desmos, right? It just tells us what that is, right? 2 comma 3, that point. So that's what we know f of 2 to be. Now let's see, f prime of 2, so what we want there, I guess, is the slope at 2. So how do we do that? Well, we first need to know f prime of x, right? So taking the derivative of that polynomial, fairly straightforward, 3x squared minus 6x plus 3. So f prime of, again, a is 2, so f prime of 2 is 3 times 2 squared minus 6 times 2 plus 3. Plugging that through and run it in, what you'll find out is that this answer is also 3. Kind of strange, but it seems like it might make sense. This can be interpreted as the slope of the function when x is equal to 2, so it has a fairly high slope right up here. I would believe that it might be 3, so just as long as I've done my math right, that must be right. So we basically have all the ingredients we need, right? We have A, F of 2. I don't actually need this one. And F prime of 2. So we have all of these ingredients that we need. So plugging in, we get that the local linearization at x is going to be f of a, that's f of 2, it's 3, plus f prime of a, so that's f prime of 2, it's also 3, times x minus a, so we'll have x minus 3, right? And what do we get? Well, you probably should simplify it to a line, mx plus b, so we end up with 3 plus 3x minus 9, so we end up with what? 3x minus 6, which, you know, it's possible, right, that thing has meets, I guess, the y-axis down at negative 6. I certainly believe that it has a positive slope and it's fairly steep. But of course, you know, the place we could go to really check this would be to just run to Desmos and see if it works, right? If we've done it right, and when we plug in this L of x equal to 3x minus 6, we don't get the right answer. What happened there? Oh. No, I had to pause there and just figure out what I had done wrong, but let's see if I can correct my error. I feel really good about the steepness of the slope of the line, but I don't feel good about, you know, it being tangent at that point. And I noticed that, you know, what it seems like is I have the y-intercept set too low. If I could move it up somehow, I might be able to. So let's go back and look again at what I did. I must have made some error on that led to that wrong y-intercept. So I think I should go back up and just see what happened when I plugged in here. I feel fairly confident that A is 2, right? That's the x value. I feel fairly confident that when I plug f of 2 in, I get 3, and f prime of 2, I get 3. So I think it's somewhere in here, and indeed it is. What I notice is that when I plugged in x minus a, instead of plugging in a right here, I plugged in a 3. I got in a hurry. So I think what this should be is a 2. And 3 times 2 then is 6. And that'll bring my y-intercept up instead of negative 6 to negative 3. Which actually, I don't know how good my drawing is, but that feels a little bit better in terms of a y-intercept. I might have, should have been probably alerted that this should have been not negative 6. So let's check that out and see if that one works. A little error in my computation. Should have followed my notes closer. Let's run over here, and instead of 6, let's try negative 3. Okay, now we're good. So kind of a nice result using our local linearization generalized, I guess, tangent line to a function at a point. We were able to get there without having to do too much work. So there's your local linearization at 3. So I guess what I could write down on my page, for the graph of the function, L of x is equal to 3x minus 3. That's your local linearization. That's the equation of course, that line right there in the graph. Okay, I feel good about that. Let's go back and see what the last piece they would like us to do. Or I would like you to do, maybe. Let's move this out of the way. Find the exact value of the error associated with the use of the local linearization to estimate f of 1.5. Okay, let's go ahead and talk about the error function. So I'll pull off another sheet here and we'll talk about the error function. So So we know that the error function associated with local linearization is e of x equal to f of x minus L of x, right? So what we're really after is the error. And we actually had a more full-blown version of this that looked like this. It was f of x minus the equation for L of x, which is minus f of a minus f prime of a all times x minus a, right? And what we're asked to find is the error associated with using this local linearization at 1.5. So we just need to plug in and find e of 1.5, right? So what we'll need to know is we'll need to know f of 1.5. We need to know this piece right here. And the x part, right, is, I guess, the 1.5 we're going to plug in. So it turns out that we can use either one of these two to calculate the error, and I think it's actually easier to use the top one because then all we have to find out is what f of 1.5 is and what L of 1.5 is, and as soon as we find those two, we just subtract them when we find the error. So let's try to find out first what f of 1.5 is. So what does f of 1.5 look like? Well, we know what f of x is, right? It's x to the third, so 1.5 to the third, minus 3x squared, so 1.5 squared, plus 3 times 1.5 plus 1. And so the number I get out when I do this on my calculator is 2.125. So that's the value of the function at 1.5. And we need to also find out what the local linearization predicts at 1.5. Now, one thing you should be thinking about a little bit is what makes sense here? We're literally sort of saying, well, here's 1.5. So if I kind of draw up here, these would be the two values of the function. The value of the function is at 2.125. That seems to make sense, right? But it looks like the local linearization will be much lower than the value of the function. So my guess is that local linearization will give me something much smaller. And we know that the local linearization line is just 3x, right? Minus 3. So I'll do 3 times 1.5 minus 3. And that ends up as 5.5 minus 3. So let's see. So let's see, 4.5. Oh, it's not 5.5. That's why I was worried. I was like, that's actually larger. 3 times 1.5 is 4.5, right? Minus 3. Okay, now we're good, right? Because then I get a number like 1.5, which, just looking at my rough graph, when I put 1.5 in, I'm getting out something close to 1.5. So I'm drawing in a fat dot here, right? I know that this point right here is 1.5, comma 1.5, and I know that this point right here is 1.5, comma 2.125. Okay, and so now we know these two functions values, and so we can just plug in here to find what the error at 1.5 is. So error at 1.5 using the local linearization is just f of 1.5 minus L of 1.5. So it will be 2.125 minus 1.5, which is 0.5 plus 125, so 0.625 is the error associated. So we're about a little over half a unit off from the function's predicted value using the local linearization. The last thing that the question asks is for you to show on the graph where this local linearization's error can be found. So this distance right here is e of 1.5. That distance right there is e of 1.5. So the error associated in using a line that's created with a tangent point at x equal 2 when we're half a unit away is roughly, well, is exactly 625 thousandths away from the value of the function. So it's the local linearization is under predicting the value of the function here. Keep in mind that error can be either positive or negative depending on whether we're above or below, in whether the line itself is above or below. And of course, the position of the line itself has to do with the concavity of the function. If we're concave up, you should expect that the error will be positive. If we're concave down, you should expect that the error will be negative. I hope that makes sense. Okay, well, that's really everything that I wanted to show you about local linearization. If you have a hard time reading these sheets while I'm, giving notes, you can look at the PDF. I'll go ahead and scan these and include them as a supplementary document to go along with this recording. And I wish you luck on your homework on this section, and I'll see you when I get back.